the series this fall term.
Oh, awesome.
Hey, everyone, welcome. Thanks for coming. Jiafei Duan is a PhD student, candidate in computer science and engineering at the University of Washington, advised by Professor Dieter Fox and Ranjay Krishna. His research focuses on foundation models for robotics, with an emphasis on developing scalable data collection and generation methods, grounding visual language models in robotics reasoning, and advancing robust generalization in robot learning. His work has been featured in MIT Technology Review, GeekWire, VentureBeat, and Business Wire. So we're very excited again to have you today. Please, the floor is yours. Take it away.
Yeah, thank you for inviting me. Hi everyone. My name is Jiafei. I'm a fourth and final year PhD student at University of Washington, and today I'll be presenting on a collection of my work, building towards this moment, which is towards robotics foundation models that can sort of reason. Please feel free to stop me if you can't hear me, or if there's any questions. Yeah, so I think my vision for robotics is pretty simple. I think robots should sort of live with us, quietly, reliably handling the mundane chores that sort of drains our time and attention. So sort of imagine like a home where the robot comes in and picks up the clutter, wipes the countertop or serves you the meal, and resets the room perfectly to its original state at the end of the day. I think the goal isn't novelty, but it's more of the point of letting people enjoy the beauty of life while the routine work are being done at the background. But to be honest, I think we are not seeing this in our home, at least not in mine. I guess the task is because the tasks that you just see in these videos are not fully autonomous. In fact, each of these are actually being remote operated by a human. So the question that I have is, what do we actually need to take in order to achieve this North Star that we have? So I think to achieve this North Star that we have, I think fundamentally we need a robotics foundation model that can understand instructions and act in a purposeful way in unstructured environments. And what does it really take to sort of act in a purposeful way? I think robots should be able to interpret instructions in context and ground that reasoning process in the physical world before it act. So a very simple example would be, imagine you ask your home robot to wipe the top right corner of the window. I think the robot should be able to have some form of spatial reasoning capability, identify the exact region, and learning how to act accordingly. Or even going beyond, whereby you ask your robot to sort of fetch you a bottle of wine, that it has stored earlier. The robot should be able to recall some kind of past actions and observations and act accordingly. So that requires some form of episodic reasoning in some manner. And even simple things like when you ask the robot to, grasp onto the grocery bag as you handing it over, the robot should be able to have this internal process of detecting whether it has have a secure grasp on the bag and sort of diagnose if something went wrong and adapt its actions accordingly. This will require the robot to sort of be able to reason over its actions and not just, taking in the perception and act upon it. So that requires some form of reasoning. So I think to really achieve what we want for this North Star, from my personal view, I think we need to, first of all, obviously have the general manipulation capability. So this includes like dexterous manipulation, the ability to sort of generalize to different environments, and even having strong instruction following. But beyond that, we need to be able to have robots that is able to, have this fundamental understanding of spatial reasoning, the idea of how do you do spatial affordance prediction, identify non-object centric actionable region that I mentioned just now, and also how do you sort of turn that reasoning capability into action in the executable task. For example, how do you wipe that the window? And even going beyond that to look at how can we sort of store our past observations and actions in the right representation such that we can retrieve it when decision depends on history. So the idea of episodic reasoning is sort of targeting this kind of non-Markovian dynamics and also kind of memory-centric actions. And lastly, I think one of the more underrated capability that I wish that my robotics foundation model will have, when one day there's a robot deployed in our house, which is the ability to sort of detect failures and the ability to know exactly what to do when this kind of failures occurs and have that kind of recovery strategy. And I think this is fundamental to deploying in everyday homes. So I think my research goal that I'm going to share today is to build this kind of general purpose robotics intelligence that can act that can reason before it act through this grounded reasoning process. And I think I'll be focusing on these three facets of spatial reasoning, episodic reasoning, and failure reasoning. And I think reasoning in this context, what I meant was to be more of leveraging a structure, inference steps to uncover implicit knowledge that generalize beyond any training pattern. And hopefully all this reasoning process that I'm going to talk about today are grounded on its action. So before we even start, we need to have some kind of concept of how people are working towards developing this kind of general manipulation capability. So I think in the traditional form of robot autonomy, people have built these custom robots, and you have like really good engineers or like technicians that can program or pre-program this kind of robot in a factory setting, and you get this really good specialized agent. But I guess today, in this kind of modern approach of new form of robot autonomy, we are looking at this kind of general purpose robots that aims to, develop or exhibit kind of general purpose behavior and driven by a generalist model. And we've seen a huge rapid progress in such generalist robot models, I think largely driven by the success of like language model and vision language model. And so it shares a really similar common architecture whereby you have encoding of multimodal observation, the task language, and the robot state, and fusing that together with a backbone LLM or VLM, and then decoding the action by aligning the vision language action and representation. And I think this recipe has shown success in driven many of these robotics foundation model, including Gemini, Robotics, Groot, Pi Zero, and even MolmoAct, which I will present a bit more. But these are all good. But the problem is that despite this breadth, today's LMs and VLMs that was the fundamental blocks towards building some of these generalist robotics model still suffer from reasoning. So, I mean, let's consider a simple thought experiment. If you give a task whereby place the green tin can in between the two plates, and you ask models like GPT-4o, you will circle the bounding box of the plate. Google's Gemini 2.5 Flash, it will also tell you the plate. Quell VL will also sort of give you a bounding box of the plate. If you use like prompt engineering with like pivot from Google DeepMind, it gives you an answer that's slightly close towards what the definition of in between the two plate means. And even if, think about if the VLMs are struggling to do this, and the VLAs that sort of train on top of these VLMs will even struggle more in terms of executing the necessary manipulation action. So this is Pi Zero, trained with a huge amount of demonstrations, even fine-tuned for this specific task, struggles to figure out what is in between the plate. Yeah. And going one step beyond, okay, I think there's something wrong with this slide. Going one step beyond, robotics foundation model today that's built on top of these VLMs are also struggling to sort of reason over its past action. So a simple example of reopening the previous drawer, you can see one of these state-of-the-art 3D-based model, RVT2 struggles to remember the action that it took just a few seconds ago. I think this is pretty straightforward because many approach today leverages on this idea of behavior cloning, which is Markovian in nature, and hence this whole task, requires some form of implicit memory, and end-to-end policies are just basically memoriness. And going one step further to look into the failures or the pitfall of reasoning for failure, I guess despite all these advances in LLMs, if you give a very simple query of this video sequence to any of these frontier VLMs, you realize that they struggle to tell you exactly what actually went wrong in this video. I think GPT does give you the right answer, but there's a 50% guess. And if you prompt it further to explain, it struggles to explain. And Gemini basically stops at yes. And open source model does even worse in this context. So there is a lot of problem behind reasoning from the VLM perspective, and eventually that will affect a lot in terms of us building robotics foundation model such as VLAs. So with that, I think today's work I will present focus on how do we sort of generate a sort of a general representation for learning spatial representation that can bridge the gap of spatial reasoning and action prediction. I'll also talk a bit about the idea of a memory-centric robotic transformer that is able to retrieve past observations and actions actions to better inform its current action prediction. And lastly, I will talk about AHA, which is a work that we look into how can we detect and not just detect, but reason about failure in robotic manipulation. So I'll start off with the first one, which is spatial reasoning. So I think the very simple answer of why existing VLMs cannot really solve that problem that I just mentioned is because a lot of these VLMs are trained with object-centric localization data set that focus on, either fine-grained or macro or micro level objects. And the question that just was prompted requires you to understand free space in a way that, to relate the object's relation in terms of free space. So the way we sort of solve this is through this word called RoboPoint, which learns spatial affordance prediction. So given the same prompt, RoboPoint will take in the observation and the instruction and output a series of 2D coordinates. And if you visualize these 2D coordinates on the image plane, you basically get a point pointing to the exact location. And I think this is the first step towards solving the task, which is to understand this spatial affordance prediction. And the way that we sort of go about doing this is that we generate spatial affordance prediction purely data purely from simulation. So the way we do it is that we use large-scale NVIDIA simulator that generates hundreds and thousands of environments, and then we systematically add in objects from 3D object assets. And because you know the object spatial reference, what you can do now is you can draw that, the grounded points on the image of the respective object, and then because it's in simulation, you can remove that object and then, re-render that whole scene. Now the points are still there, and you have this kind of spatial reference affordance related to the language description of the other objects in relative to that point. And with that, we're able to do full instructional fine-tuning of, in this case, Lava 1.5, to be able to train a spatial affordance prediction model, VLM, that's able to take in natural language instructions and output the corresponding points that refers to exactly what the instructions is referring to just training on this synthetic data. And RoboPoint is really good because RoboPoint is able to sort of point for spatial affordance. So given an example where you ask, you ask RoboPoint to place the orange on the bottom step, given just this observation, RoboPoint will be able to generate this sequence of 2D coordinate points. And then using a bit of the depth from the RGBD camera, you're able to get a 3D point with motion planners. You're able to move the robot to the exact position that you want. But obviously, going beyond just using for manipulation, I think we also show that RoboPoint is a general purpose enough VLM that you can actually use it for other purpose. For example, AR assistance, whereby if you ask RoboPoint, how do I get to the carpool lane? So for those people who live in the US, you know that the carpool lane is always on the leftmost lane, and RoboPoint's answer will be to the left of the leftmost car. And then you can tell RoboPoint to go to that position, and then in a view consistent manner, you will keep generating the points referring to where the exact location that you are trying to localize. And lastly, we can also use RoboPoint for navigation. If you want to navigate to the free space in front of any specific object, RoboPoint will be able to draw the points, and you can have your own robot system that does the navigation, that takes in points as an intermediate representation. So I think pointing sort of started also this whole line of work that focus on using intermediate representation to sort of steer low-level policy. And I think one interesting emerging property is this view consistency, whereby now if you are rotating your viewpoints, the view dependent relation does not change. So for example, locate the right side of the blue card, it's always going to be that same right side of the blue card, no matter how you rotate your camera. And I think the interesting thing about RoboPoint, or this concept of pointing, since RoboPoint is the first paper that proposed this notion of pointing for spatial reasoning, is that many of these frontier models over the past 2 years, it was inspired by RoboPoint and the release of RoboPoint's dataset. And you can see based on this paper that systematically evaluated pointing capability in all these VLMs, you can see that there's a huge surge of performance since the release of RoboPoint. And pointing has been one of the key features in many of these frontier models that supports many downstream applications, including web-based agents. And for robotics especially, I mean, RoboPoint has been integrated into NVIDIA's hardware as a starting tutorial session for NVIDIA Jackson. But I want to go a bit beyond that. Like, can such spatial representations of go beyond pick and place? I think the answer is no. If you ask RoboPoint to pour you a cup of tea, RoboPoint will just generate 2 points, and that's it. You can't do anything with these 2 points. It's useless. But the idea is that we need to have a plan to sort of steer our low-level policy. I think for roboticists, we know that to go even further, we need to have some notion of depth also to help us reason over our action, especially in a closed perception control loop. And even going one step further to say, I don't think you can sort of reason over these actions just via language. If you use the latest GPT model and you give the same task, it generates a pretty nice detailed plan with like executable steps that it thinks could execute. But we try it personally, nothing on this plan actually work. So obviously, because none of these are grounded, you can't ground plans through language for robotics. So with that, we introduced this new word that came out from AI tool, It's called MolmoAct. MolmoAct is a first of its kind. It's an open action reasoning model, and the whole idea is that it's an autoregressive model. Given the same natural language instructions and the observation, MolmoAct will first of all output these perception tokens, and if you decode this perception token, you'll basically get a really nice depth map, and you can visualize the point clouds using that depth map. And condition on that, we will then generate this visual reasoning trace. And this visual reasoning trace, when you try to visualize it in 2D space, you will actually get a plan forward at that time step, telling the robot exactly what to do. And this plan is interpretable to humans because it's just a line that sketch. And then condition on this, you're able to generate the necessary robot control actions required to actually solve this task, which is to pour me a cup of tea. And because MolmoAct is largely pre-trained on a huge amount of robot data, we evaluated MolmoAct's pre-training capability through this evaluation suite of Simpler, which was developed to match the training distribution of the common data set that everyone is using, OpenX embodiment. And it's interesting to find that MolmoAct is actually one of the state-of-the-art models out there, outperforming all these other models from the different frontier labs. And more interestingly to know is that MolmoAct is able to outperform models like Pi0 in Simpler which is trained with 39 times less data, or even with NVIDIA's GRU M1.5, we are training with 26 times less data. And the secret is no secret. I think the secret lies in data. But one of the tricky part about this whole project is that one of the mission of AI2 is to focus on open science. So we are sort of bounded to use open source data set. And for many of you who have used OpenX embodiment, this is a great effort collected by many institutions. And it's one of the largest open source data set that's out there. But the problem is that we need to have high quality data set and not just quantity. Not just quantity. And the problem about OpenX embodiment data set is that you will get data points that looks like this, which is really low quality in terms of visual resolution. Many of the visual encoder itself is higher than this. And even you have real and no language instruction of the robot doing random stuff. And for like large data sets collected by Google, you have video sequence of almost 9 seconds of the robot not moving at all. So if you convert that into frames, that's over 100 plus frames of no ops. And you have recent data sets like Droid, which has actions basically just grasping thin air. So I think there's a lot of existing problem in OpenX embodiment dataset, but it's definitely a good platform. And the first thing we did was that we filter out all the data set. We spent a lot of manual effort to try to do this, to remove the weird instructions, remove those scenarios as no ops. And we were able to filter it all the way down to 119,000 really good high quality data out of 1 million trajectories. But obviously with this is not enough. So we actually collected some in-house data at a small scale. So we collected about 10,000 high quality robot episodes over the span of 2 months. And this focused on like really different household tasks. We rented different Airbnbs to try to collect this. And also beyond that, we also collect really good atomic skills. These skills could be like try to place the plate on the stand by rotating it. And the notion of this is to focus on collecting 100 skills or 100 tasks, in this case that has repeated demonstration. So the distribution of it is that every task you can train an independent diffusion policy, and hopefully that will work. And even with that, we are still far away from what Pi0 has been trained on. So if this, we have MolmoAct is trained on 200K robot episodes, whereas Pi0 is trained on 1.2 million robot episodes. So what is the secret to sort of, have this David versus Goliath effect? So I think the answer is in reasoning. So I think LLMs have shown success in intermediate chain of thoughts to reason, and reasoning in language is kind of ambiguous for motion in space. So we argue that robotics needs to be able to reason in space. And the way we do reasoning in space is by curating this action chain of thought data set that can be grounded. And the way we do it is that given a robot sequence, a trajectory sequence, we first use MoMo, which is our VLM model, to point at the gripper. And then if you try to combine all the points together, you basically get a trajectory line that's sketched forward in time, telling you what's the next sequence of action that's required, for the robot to take. Obviously, just with this, sorry. Oh, is it? Oh, okay. Yeah. So even if just this, it's not enough. We need to be able to do reasoning in 2D pixel. Reasoning in 2D pixel is not enough. We need to have some kind of 3D or like depth information. But obviously, a lot of this data are collected just on RGB alone. So the way we do it is that we train MolmoAct to incorporate this perception token. And the idea of perception token comes from the paper that's mentioned at the bottom, whereby you train a VQVAE that takes in this kind of image that's passed through depth anything to get relative depth. You have an encoder decoder, you obtain this perception token, and use this perception token to label all the rest of the RGBD image. And putting these together, we're able to formulate this action reasoning dataset, whereby now the model will be able to, first of all, predict the depth tokens, and then condition on these depth tokens tries to predict the trajectory reasoning tokens in 2D, and then using that to condition on predicting the action control. And obviously, we also use retain Momo's visual reasoning, visual reasoning capability for MolmoAct through these other datasets. And this is just a overview of the data set that we use. Obviously, we use more auxiliary depth data. We also have auxiliary line data. And we have this trajectory condition data that sort of teach MolmoAct to be able to be steer, which I'll cover a bit towards the end. And training and inference with MolmoAct, I think pre-training, the first stage we train, which we start with pre-training. The idea of pre-training goes from Momo as an initialization VLM. And then the idea is to focus on these 119,000 robot episodes to try to learn world knowledge or basic action understanding. And then we have a mid-training process whereby we try to learn actions from very specific setting, focusing on high quality data. And this seems a performance gain of 5 to 7%. And then focusing on the last part, which is post-training or fine-tuning, we try to learn to dynamically adapt to new downstream tasks or different embodiments. And the way you can prompt MolmoAct, you can do reasoning in space, which is this autoregressive method of predicting control actions. Or there's also another way to prompt it is you can try to steer the action, which I'll cover a bit later. And post-training evaluation, we show that MolmoAct is able to solve many of these downstream tasks across various different embodiment. And I think also one interesting fact is that when comparing simulation benchmark like Libra 10, we show that MolmoAct, at least compared to all the autoregressive model that's out there, is one of the state-of-the-art performance. And many of these autoregressive models are also what we call reasoning models. And the question is, how much does this grounded reasoning actually helps MolmoAct? So I think if a simple experiment that we actually conducted on a variance of MolmoAct looks into evaluating on simpler, we found that if you have just MolmoAct itself, you get pretty good result. But if you remove the depth, the performance starts to drop. And if you remove the depth plus line, the performance drops further. So suggesting that the grounded reasoning process or this action chain of thoughts really does help the model to actually improve its action prediction. And is MolmoAct really doing reasoning? So I think that's also a question that we have. If you look at existing VLA models, the moment they are trained with actions, they basically lose everything that is required to do basic reasoning. So basic reasoning in a sense where we are answering VQA questions. Whereas MolmoAct is one of the only model that actually still stands in the test of all these different multimodal VQA questions, suggesting that it did not suffer from catastrophic forgetting. And one other interesting fact is that we are able to steer MolmoAct. So, given arbitrary language instruction, like for example, put a toy onto the coaster, it could be any coaster, right? So, how do we actually steer that? So, the policy, because it's predicting forward in time, it tells you exactly what is intent, making it really interpretable. So, you might want to go the coaster to the top right, but after you pick up the toy, it wants to change its plan and go to the one at the bottom. Now humans can come in and draw a line to use that line to sort of steer the direction of MolmoAct towards the top coaster, which is as always intended by the user. And we also show that open instructions steer MolmoAct less, not as great as using this kind of visual reasoning trace that you can just simply sketch out. And we also tested this with other models besides MolmoAct, for example, Pi0. So I think with the release of MolmoAct, we have seen like huge downloads of the checkpoints and model, and also folks are being like start to deploy MolmoAct and inspire many other works that looks into reasoning-based models, even with recently Gemini 1.5 that focus on reasoning before it act. So I hope that for the first part, I'm able to sort of showcase that MolmoAct's capability, which is that by defining this chain of thought process for robotics. Through this reasoning in space, we enable MolmoAct to sort of surpass baselines with much less data. And I guess language condition pointing for spatial affordance is also one beginning step that helps to yield really powerful intermediate representation for robotics. And I'll move on to the second part, which is episodic reasoning. I think this is a very simple illustration of what people have been doing for policy learning in robotics, mainly focused on imitation learning. I think I will not go deeper in depth into this, but the whole idea of the notion is that you want to maximize the parameters for your policy in such a way that you can predict the best action condition on the observation and the task conditioner. And in robotics, the observation could be RGBD and the task conditioner is natural language, and you also have robot action. But the problem about a lot of this is that many of these imitation policies are memoryless. And in fact, most of the robotics manipulation policy doesn't even require memory. And I think the fact is because we all have this Markovian assumption in mind. So if you look at a 3D-based behavior cloning policy like RBT2, if you give a very simple task of pressing the button that with the blue cube in front of it twice, after policy pressed the first button, I remove the cube. And these are all part of the demonstration. You realize that RBT2 struggles to figure out where's the button, even though it's just like literally 2 seconds ago. So the way we sort of solve this problem is that we propose this model called SEM2Act, which is transformer-based robotics policy that is able to address this memoryless problem. And the way we sort of address this is to first have a strong multitask behavior cloning policy. So if you see from the video where we do the same task, SEM2Act will be able to retain its memory, and that's because it figures out what's the right representation to store these past actions and observation in a computationally tractable way. And for this task, we have almost 100% success rate. And the way we do it is through this two-stage training for this memory-centric robotic policy. And I think SEM2S, and the way we do it is that the first stage, we use RVT2 as the base backbone, and then we basically incorporate the SEM2's image encoder for better visual representation before it goes into the multi-view transformer. And then we also introduce this multi-resolution upsampling technique, whereby we are able to leverage the resolution that comes in from the SEM2's image encoder to enhance the prediction of the action heat map. So the notion here is to say that, if the model can perceive much more precisely, it can act better. And that's true when we evaluate it on the R bench 18 tasks. We've shown that across these 18 tasks, we are able to achieve state-of-the-art performance at that point in time. And then for tasks that's really hard, for example, insert pick, for many iterations, none of these models are able to make significant progress in the performance. And I guess SEM2 is able to solve that task pretty well. So for example, this task of inserting pick requires millimeter precision in terms of how you insert. SEM2 is able to do it. Or even in the real world example where you're asking it to turn on the lamp, RVT2 will often miss by a few millimeter, resulting in not able to succeed. And even beyond that, SEM2, because with the image encoder that's really good as compared to all the other image encoder for robotics, we found that SEM2 is able to generalize really well to this benchmark called Colosseum. When it's test on out of distribution during test time, it has the lowest amount of perturbation drop. So what it means is that now you could introduce a bunch of distractor, and then given the same task that SEM2 needs to do, SEM2 is able to solve that task pretty well. So with that, we show that a strong multitask behavior cloning policy that's robust and generalizable enough is able to be now then adapted to become SEM2Act Plus, which focus on adapting this memory architecture for remembering past action. So I think remembering past action could be more trivial if you're using like a traditional recurrent network. But the problem is that right now everyone is sort of empowering their robotics model with like this transformer architecture. So how do you sort of represent and remember this past action matters a lot. So the way we sort of do is that we introduce this memory architecture inspired by SEM2 in such a way that every time after the multi-view output is embedding, we will then attend with the memory attention together with what is stored in the memory bank before doing that multi-view upsampling to predict the action heat map and then decoding it back and storing in the memory bank. So essentially what this is doing is that it's enhancing its action prediction with a concatenation of all the past experience that the robot is remembering. And obviously, we want to make sure that when we test this, we are testing this in a more scientific way, whereby we decouple the concept of long horizon tasks, which most of the behavior cloning policy tends to fail because of compounding error, but focusing on only the notion of remembering and having this concept of memory. So we keep our tasks really short, but intentionally trying to break the Markovian assumption. So for example, the second task here, which it says put the block back, the block is started from any of these random 4 patches. you put it in the center, you press the button to sort of break off that state, and then you try to remove that cube back into the position that it's originally started from. And as you can see, because that's 4-patch, policies like RVT2 aim to achieve around 25% success rate, while SAM2AI is able to go all the way up to close to 100. And I think hopefully, with SAM2AI, we have sort of inspired a huge line of work that focus on, this memory-centric kind of policy learning, especially in the era where vision language models are mainly driven by this whole notion of imitation learning. And I think that's the summary of episodic reasoning. And I think moving on to the last part really quickly, I think for failure reasoning, I think this is also a very interesting topic that I find very, personally, I really like it. So I think many of the robotics system today leverage LMs and VLMs to automate some parts of their system. So these are just some example of the paper that's been published in the past, I think, 2 years. Obviously, there's more than 100 plus of these kind of papers that leverage LLMs and VLMs to automate some components of their system. But today I'll talk about specifically one, which is Eureka. Eureka is one of the work that's more well-known. Eureka actually leverage on LLMs to generate dense reward function that aims to surpass human level performance. And this is a work from NVIDIA. The idea is that given the state information of a task in simulation, you use language model like ChatGPT to generate a dense reward function, you train RL policy, and you train many of these RL policy, in fact, and then getting the best reward, and you refine on that. So essentially, if you think about what Eureka is doing, Eureka is basically doing a search. The idea is to search for the best reward function in an iterative manner. And the good thing about this search is that eventually you will find a reward function that might work. But the bad thing is that many of these LLMs are closed source models that you cannot be able to actually make huge change or even diagnose actually what went wrong. So one example of Eureka for this task of opening a door, after 16 iteration later, the door barely opens. But if you change your perspective and think of this problem slightly different, if in one step a human looks at the rollout trajectory and identify what fundamentally is wrong in terms of the action and give that feedback towards generating the next iteration reward function, then we are able to actually solve this task pretty quickly. So to do that, we actually replace that with AHA, which is a vision language model that's able to detect and reason about failure. And in just one iteration step, we are getting much better behavior compared to 16 iteration later. And the problem about this is not a tough question. In fact, it's very trivial. Failure is actually very often in robotics, but to label failure is really hard. So imagine a trajectory that looks like this. We always see this during experiments, and when our policy fails or the gripper slips, it's really hard to label this. And if you use human to label, there's no way you can do this. So coming back to simulation as a channel or a medium for us to actually generate data for failure trajectories. So the way we do it for AHA is that we actually use this concept of procedure generation. So we take successful demonstrations, it can be from any simulator, of tasks that actually work, and then we systematically perturbate all the keyframes and create this based on our taxonomy of failure modes. And then we will supervise and see which of these episodes end up in failure trajectories at the end of the day. And then because you know exactly what you actually perturbate, you have the ground truth explanation of why it fails, and then you're able to generate this VQA pairs of failure trajectory sequence with an explanation of why it fails and whether it has failed. And using the same training paradigm, together with co-training, we're able to fine-tune AHA to be AHA 13 billion, which is a VLM model that now takes in a sequence of observation and outputs the explanation of why the robot fails. And AHA is able to detect failure for this example in a very similar way that humans will be able to explain. And beyond that, we evaluated on not just in distribution of what we are trained on, that simulation, we also evaluated on real-world data sets like a robot fail from Stanford, or even a different domain completely from Maniscale. And I think the result is really promising. We show that AHA is able to generalize much better in terms of across all these different benchmarks, not just on one metrics, but on 4 different metrics that evaluates binary success, and also even in terms of like semantic explanation of why it fails. And then I think the idea is what can you do with a VLM that can sort of detect and reason about failure? So the first thing you can do is you can solve Eureka. So you can use this redesigning of reward functions to improve RL in a way that now, in the same manner, if you have Eureka trying to propose an initial reward function, all you need to do is let AHA look at the video sequence, generate an explanation, feed the explanation back into the LLM, and then re-author the dense reward function, and you are expecting to solve the task in maybe one step. You can also use it for task and motion planning, whereby now in an open vocabulary setting, you use language model to generate a plan before you pass into a temp system. AHA can look at the rollout trajectory from the temp system and assess whether how good is this plan, and then make edit upon it. You can also use it for reward modeling for VLM RL training. You could also use it for step-by-step open vocabulary data generation. And I think this sort of inspire a whole line of work that focus on failure reasoning going beyond just binary detection, which what we have been doing for quite a period of time. So I think for the failure reasoning conclusion, I think we sort of show that, direct sim to real transfer is feasible at semantic level, at least for when it comes to, example of reasoning over failure trajectory, and reasoning about failures for robotics sort of offers a better initialization and a more grounded approach for robotic system that leverage on LMs and VLMs. And I think hopefully with that, I come to the end of the talk and summarize, and you are convinced, at least there's two things. First of all, we need to have this kind of understanding or semantic knowledge drawn from LLMs and VLMs to sort of help us to build this robotics foundation model. And secondly, I think the way forward is to actually empower our robotics foundation model with this reasoning capability. And obviously, I only show three kinds of different reasoning capability. I feel that there's many more to actually come. So hopefully, that I convince everyone there. And I think that's it. So thanks to my collaborators and mentors. And I'm also on the job market this year. Yes, I'm open to take any questions. Oh, I can't hear you guys clapping, but yeah, I can see.
Okay, wonderful talk. Jiafei, can you hear me?
Yeah, I can hear you. I can hear you. Yes.
Okay, let's just take questions from people around.
Let
I
me
have
check.
I have a few questions.
Oh, yeah.
Hi, it's Liam. So, I have a sort of specific question about that ablation that you showed over to justify the reasoning of MolmoAct compared to Pi0. Can you explain a little bit how you ran that ablation? Like, how do you actually take Pi0 and evaluate it on a BQA data set?
This is Pi 0.5.
Yeah, sorry. Yeah, so this thing is outputting action tokens. Like, how do you actually is it simple to
Yeah. So there's so if you look at Pi 0.5, they have a pre-trained version, and then the pre-trained version is purely fully auto-regressive. And the post-training, there's two variants. So you can also output auto-regressive tokens, and also at the same time, you have these action experts, and you can feed the embeddings into the action expert. So there's two modes of prompting Pi 0.5. And because Pi 0.5 is trained with multimodal data during co-training, so in that sense, you can actually see results in terms of the reasoning capability if you try to answer some data.
I see. Interesting.
Yeah, and also this result was also checked with another work that came out recently. I should probably cite it here, but yeah.
Okay, interesting. And my next question is about the memory structure that you're building.
Okay.
So I think you show that so you have kind of a static orthographic projection of the scene mostly. And the types of memory that you're showing are memory about the way that the scene is changing. But do you think that this type of approach would also apply to the case where your camera is moving and you're seeing things, and then you have to keep track of the things that you've seen in other parts of the environment, like a more kind of mobile slam kind of version of memory? Do you think that this would work or not? And if
so that's a really good question. So the answer is no. So I think this focus on more short-term spatial memory, memory that is inherently you are essentially you are looking for like a policy, right? So like for example, if you have a high-level planner, there's always keep tracking memory in terms of like using language or semantic, then you might not need this. But if it's just an action that you took instantly, you want at least the policy to be able to remember the action. So I think for short spatial memory, SEM2 will work. But for like mobile manipulation, where you are talking about like really long horizon sequence, then I think there might be a different formulation. And I think the thing to also think about is that a lot of these VLA models are moving towards having like a ability to output taking high level language instruction and output this kind of subtasks. And then the subtasks are driven by the actual predicting the necessary action. So you want that component to be able to actually have some kind of implicit memory so that at least it doesn't remember within that one subtask what it's actually doing. Yeah. So I think that's the focus here. So the answer is no. Yeah.
That makes sense. That makes sense. Yeah. Very interesting work. I don't know if other people have.
Also have a quick question about SAM2ACT. So what exactly are again the purple images that you saw put in during the first stage of training? At the top part of the diagram?
This
sorry.
one.
Yeah, exactly.
Okay, so maybe I should also cover a bit of background. So SAM2 was built on top of RVT2, and the way RVT2 does is that after the embedding that goes into the multi-view okay, so SAM2 so RVT2 has no multi-resolution upsampling. It's just a one-time convex upsample. So the after the observation goes into this multi-view transformer, it predicts embedding, and then when you do convex upsample, you get back this dimension of like basically matches the exact same as the input, but with only one point that's highlighted, and that one point represents the action point. So imagine if this is multi-view and you have all the camera position, you can concatenate these different viewpoints together and get a point in 3D. And that's like a next point that you want to sort of move your robot to as the next 3D point to predict. So that so they call it an action heat map in that sense. Yeah.
And that's the information you are using as your memory, then like the past sequence, I guess, of actions in 3D space encoded by this, right?
Yes, because this action heat map is a cross attention between the observation and the action. So we use that to encode it using our memory encoder and store in the memory bank. Yeah.
I imagine you're also like bounding. Sorry, to interrupt. Go ahead.
Oh yeah, and also to mention is that SAM2 have focus on like this kind of keyframe based behavior cloning approach where you're just sort of having like keyframes and using motion primitive to bridge that keyframe rather than action based models where you predict like every time step with a certain control frequency. And I think the problem, also the limitation in this case, is that SAM2 has a context window, and the context window is depending on the largest sequence in the multitask training. So for example, if you have like 10 tasks, the context window is probably the largest task of the 10 tasks. Yeah. Sorry, what was your question?
No. I was basically going to ask about the memory, but let's leave other people ask questions if they have. If otherwise, I'll come back. Anybody else?
Sure.
People online?
I can't see people online, but yeah. Oh, there's people online. Okay.
I'll ask my other question.
Sure.
Did you make any experiment about the relation of? I imagine you bounded your memory bank, right? Like, what is the relation you have? Like, I don't know, memory requirements versus the amount of information you can preserve in your memory over time. Like, yeah.
Sorry, I didn't quite catch the question. Okay, do you mind repeat?
Like, did you make experiments about the memory requirements to store a specific amount of time in your memory? Like, I don't know, I need 100 megabytes to store 2 seconds to 2 minutes of the previous information that was already executed. You have it to have them.
Yeah, so we don't have an implicit experiment to show that, but the problem about this also is that it's a sort of a two-body problem, right? So if you look at some of these tasks that we designed, these are really short step tasks. That means you probably have only like 3 or 4 keyframes. And why we design implicitly in this way? Because if we don't do that, we design long horizon tasks and you do multitask training, you realize that a lot of the baseline models could not even finish the task completely.
I see.
Yeah, and then that's the problem, because if that's the case, then do you say that it's not remembering because it can't, remember, or it's just because it's not capable of solving the task? So the way we sort of do it is that we keep it short and we really focus on the key aspect, whereby we want to sort of say that, in a counterfactual argument, whereby if the model does succeed, it will always fail because of memory. So that's why we keep it short. Yeah. So as a result, we don't really have like sequence of like really long horizon tasks with a huge context frame. Yeah.
Thanks, Jiafei. That's really good.
Thank you. Yeah.
I have maybe a slightly more high level question. So
Yes.
if I understand correctly, like the majority of the experiments you've shown are in Isaac world, right? Like the simulation is all in Isaac, pretty much, I think, right? Correct? Yeah. And so I think you're making the argument that like especially in the failure case that like semantic reasoning is going to transfer sort of zero shot from Isaac to the real world. And
Simulation
you're
to
showing,
yeah,
Pardon me?
I don't think it's Isaac specifically. I
right,
think
but simulation, but also like that Isaac is like sufficient, has sufficient like semantic expressiveness that it captures the kind of semantic information that you want it to learn so that it can be transferred. Like that's not maybe true of every simulator out there, but there's probably others, so whatever. But then, so like, how do you, so you're viewing this like zero shots into real transfer at the semantic level, but then you've also shown a lot of examples of skill execution. And so how are you viewing this into real transfer on that part? Like, are you doing fine tuning on the real robot, or are you also expecting that the actual like low level skill execution is going to transfer pretty much zero shot? Because the requirements now of your simulator are like a lot different and probably more severe for the low level skill execution than for the semantic reasoning part. I don't know if I'm making sense.
Yeah, I sort of, I sort of get what you're trying to say. So I think to answer that question, I think is really interesting because one of the things that we found in our work with like RobotPoint or AHA, which is that what you exactly just say, right? Semantic this kind of semantic reasoning capability, it can be transferred from manipulation sim to real. And obviously sim to real has been sort of also something that people that works on grasping is able to see, like a lot of contact GraphNet and all this work from NVIDIA that shows that. But I think learning like more implicit low-level control, like in terms of action, I think we have not really figured that out yet for how you can sort of do sim to real. Maybe there's not enough data, or maybe the way we scale data in sim is not correct. But I think the idea is that at least for a semantic level, you are able to transfer because you are sort of extracting a lot of like this kind of real world more detailed representation, like for example, the understanding of like very precise contact, or even like how you actually manipulate the object. But it's more of like the overall idea of how failure occurs. So that when the robot is slightly above, then that's definitely is missing that grasping pose. So in this kind of visual context, I think it transfers really well. And also in another context where we look at a robot point where you just transferring the capability of pointing. I think I think I did show one example which is the one I used this is me driving down Bellevue in Seattle. This example of me driving down Bellevue in Seattle. Nothing in this image was ever seen during training for simulation. Like the simulation that was used only focused on kitchen. So how did that transfer? So I think there's two aspects, not just the simulation from the synthetic data from simulation, but also this large scale pre-training that comes, when you try to pre-train some of these VLMs, also together with some co-training of like world knowledge data sets. So I think this phenomenon occurs because of that. And same case goes for AHA. We see that generalization of semantic transfer because of this large scale training. So I think there is also like this large scale training that plays a huge role. And I think for GraphNets or like contact GraphNet, they also show that when you have enough amount of this grasping data, and your representation is not that complex, and you focus on just using point cloud, then naturally that will transfer. So I think but the problem is that for low level actions where you're just only using RGBD, I'm not exactly sure how that sim to real will actually work at this point in time. I think people also trying to figure that out. Yeah.
Yeah, thanks. That's interesting.
Yeah.
Great. I think that's it.
Okay, cool. Yeah.
Thanks a lot again for accepting the invite. Jiafei,
No
good
worries,
touch.
yeah.
Great, impressive body of work. Yeah, thanks again a lot.
Thank you. Yeah, thanks so much. Yeah.
Good luck with the job search.
Yes. Yeah, that's the last slide trying to promote a bit. But yes, thanks.
Thanks.
Thank you. Okay. See you guys. Bye.
Yeah.